Good morning, class. I'm sorry I'm late. I had to restart my router not one, but 2 times in order to get my internet to work this morning. And I didn't realize I didn't have internet until just before I started the lesson. So, okay. So this is April 1st, computer science. Okay, so I'm going to start off with a fairly simple neural network. Okay. So this neural network is going to have 3 layers. Okay, so here's layer 1, here's layer 2, here's layer 3. And each layer has only 2 neurons. Okay, so I'll call this 0 and I'll call this 1, 0, 1, 0, and 1. And so we have some link weights. Some links connecting. So this is layer 0. This is layer 1. This is layer 2. Okay, and so let me give the link weights. So 0.3, 0.1, 0.5, 0.7 for so just to remind you of the notation that we developed in the last class. So this right here, this is the link that connects, this is the link right here that connects neuron 0 to neuron 0, neuron 0 in layer 0 to neuron 0 in layer 1. So that is W, and then we put a little parentheses, 0, 0, 0. Okay, so this is connecting layer. Okay, so let me just do another one. This one is connecting neuron 1 to neuron 0, so this is W10, and it's going from layer 1 to layer 2. So that would be the symbolic name for that link. Okay. So then we have some links here. 0.2, 0.1, 0.3, and 0.4. Okay, so let's do a practice of propagating a signal through the network. Okay, so let's suppose that our input signal is 0.8 to the first neuron and 0.2 to the second neuron. Okay, so now the 0th layer does nothing. It doesn't apply the sigmoid function. So it literally just, the output of the 0th layer is just whatever the input was. Okay, so it just passes on the input. And then if we want to know what is the input to the next layer, well, we look at the output of the previous layer and we multiply by the links leading in. Okay, so this is going to be 0.8 times 0.3 would be 0.24. So we're going to get 0.24 from this link. And then from this link, we have 0.2 times 0.5, which is 0.1 along this link. So the total input to this neuron is going to be the total input to that neuron is going to be 0.34. So now what I do is I apply the sigmoid function to that to get the output of that neuron. So 1 over 1 plus e to the negative 0.34. And when you do that, you get an output of 0.58. Okay. I already have this written down on another piece of paper because I wanted to double check my math before proceeding. So now let's do this neuron's input. Well, it gets 0.8 times 0.1 for this one. Okay, so that's going to be 0.08. And then it gets 0.2 times 0.7 from this link, and it's going to be 0.14. And so this neuron has a total input of 0.22 because we add these two numbers. And if you apply the sigmoid function to that, you get an output of 0.55. Okay. So then doing the same process, we get that the input to this layer is 0.281, and the input to this, we'll just call it 0.28, and the input to this one is also 0.28. And then you apply okay, so now you apply the sigmoid function to those, and you get 0.57. All right. So, now here's the next idea. So this is all review from what we did last time. So that's called feeding. It's called propagating a signal through the neural network. Okay, but the whole idea of a neural network is it's supposed to learn things. So let's suppose that the neural network, when given this input, it has a certain target output. So let's suppose that the target, okay, is for this output to be 0 and for this output to be 1. Okay? So the error, okay, of the output is equal to the target minus the actual output. Okay, so what we have here is we have an error of, if I subtract these two, 0 minus 0.57, that's an error of minus 0.57, and then 1 minus 0.57 is an error of, I gotta draw these neurons bigger. So this is neuron 0, this is neuron 1. This one has an error of 1 minus 0.57, which is 0.43. Okay, so that is the error. Now let me draw the rest of the network. And so the idea is we want to use the error to update the link weights. Update these numbers, 0.2, 0.1, 0.3, 0.4, 0.3, 0.1, 0.5, 0.7. Update those numbers so that the output is going to be closer to the target. Okay? So that's the whole idea, is that we feed the neural network an input, and then we see what the output is, and then we have a target output for that input, and we use the error between the between the output and the target output to readjust all of the link weights so that the neural network better models reality, or what we want it to do. Okay? So I'm going to redraw this. Okay, so let me write down these links again. Okay, 0.3, 0.1, 0.5, 0.7. So now the thing is this. So we can use these errors to adjust these 4 link weights. Okay? But what we need to do is we also want to adjust these 4 link weights. So we need to carry this error backwards through the network and see what is the effective error for these 2 neurons. Okay? So you need the error to adjust the links in the layer just before that. All right, so we have to do what's called back propagation of error. Okay, so we're taking the error in the output and we're converting that into errors in the outputs of the previous layers. Okay, so what you do is you just go backwards in the same method. It's like going into a neural network but going in the backwards direction. Okay, so if we want to know what is the error of this one, it would be 0.43 times 0.1 plus negative 0.57 times 0.2. So it's the signal going backwards in the exact same way. Okay, so we run the neural network backwards in order to get the to back propagate the error. So if I do that, so for example, this error is going to be, so the error of neuron 0, this is neuron 0 in layer 1, is going to be equal to 0.43 times 0.1 plus negative 0.57 times 0.2. Okay, and so that error is negative 0.07. Okay, so I'm going to circle these errors so that they're more clear. And then if I do the same thing with the other one, I have, so the error of neuron 1 in layer 1 is going to be negative 0.57 times this link, which is 0.3, plus 0.43 times this link, which is 0.4. Okay, and so what I get is okay, plus negative 0.57 times 0.3. I get a very small error for this one of 0.001. Okay, so now I have these errors. And so now what I'm going to do is going to give you an equation, and I'm not going to derive this equation. Okay. So if you want to see me derive this equation, it involves calculus, and so if you want to see me derive the equation, come see me during office hours or something like that, and I can show you. But the whole idea is we're trying to minimize the error. Okay, so you can imagine if you're in calculus that that's a very calculus-y problem. It's a minimization problem. And so there's a formula for how each link weight is going to change. Okay, and this is the formula that looks scary, but it's not that scary. Okay. So it's A times okay, plus 1 minus O plus 1 times OI of L. Okay. So this is our equation, and it's in the assignment. So if you don't write this down, it's okay because it's in the assignment. So this is the change in the link connecting neuron I in layer L to neuron J in layer L plus 1. That's what this notation means. A is something called the learning rate. Something just vibrated. I get a message. It's called the learning rate. Okay, and so that is a free parameter. So it basically, the idea is with a neural network, you give it a lot of inputs and target outputs. And if the learning rate is large, then the neural network is going to change very rapidly. The link weights are going to change very rapidly. That is an advantage because it will learn faster, but it has a disadvantage in that it's a larger learning rate is going to make basically the neural network is more sensitive to much more sensitive to the most recent input. Okay, so basically it learns so fast that it forgets everything else. So you kind of want like a middle ground learning rate. So we're going to choose a learning rate, and again, this is a free parameter of your model. okay, of your neural network. So you get to choose what it is. And I'm going to say that the learning rate for our neural network is 0.5. Okay? So what I would like to do is I would like to adjust these weights first. Okay? So these are the weights that are coming from layer 1. So I'm going to do all my delta W's. Delta W, and this is coming from so I got 4 delta W's, and I've got the change in the link weight connecting 0 to 0. So that would be this one right here, because that connects neuron 0 to neuron 0. The one that connects neuron 0 to neuron 1, that would be this link weight right here. I have the one that connects neuron 1 to neuron 0. And then I have the link weight that connects neuron 1 to neuron 1. Okay, so I have all these formulas. So you can see why it's nice to have a computer to do this, because this is going to be tedious. In fact, I didn't have time to complete the calculation before the lesson, so I hope I did this right. So notice how all of them get multiplied by the learning rate first. So that's 0.5. The next thing is the error in the layer in front. Okay, because see how this is L and this is L plus 1. So because we're talking about layer 1 here, we're talking about these errors. All right. The error in the layer in front of this, of the second index here. So J. See how that's J. All right. And so I have, so here's 0 is the second index. So if I look at the error of neuron 0, it's negative 0.57. Here I have index 1, so it's the error of neuron 1, so that would be 0.43. Here I have 0 as my second index, so it's going to be negative 0.57. Here it's 1, so it's 0.43. So now I've taken out that term. Then I have the output in the layer in front. So the outputs are these two numbers, right? And so it's in the layer in front, and again it follows J, which is the second index. So the output of 0 is 0.57. And then notice how I have times 1 minus the same thing. So I have times 1 minus 0.57. This is going to be, actually all these are going to be the same, because and the reason is that the output was the same for both neurons. Okay, so that you'll have a different one in each, because it does depend on J. But and then we have the output of the layer. So these were the outputs of the layers of the I index. Okay, so notice how it's L. So it's the layer. It's not the layer in front. See how it's not L plus 1. So this would be the output of layer 1 essentially, and then we're going with the I index, which is the index in front. Okay, so the 0th output of layer 1 is 0.58. So this is going to be 0.58. The 0th output of layer 1 is 0.58. The 1th output of layer 1 is 0.55. And this is also 0.55. So now I have to do this calculation. So give me 1 second to compute this. Again, I wanted to do this ahead of time, but I just did not have the ability to do that. So this one has a change in link weight of negative 0.33. This one has a change in link weight of 0.03. This one has a change in link weight of minus 0.04. Oops, I goofed on this one. It should. I felt like this one was way bigger than the others, so this one's also minus 0.04. This one is plus 0.03. So what we should do is we should update these link weights. So this one is updating 0, 0. That's 0 to 0, and we can see that link weight is 0.2. So I should change that one to 0. So I should subtract 0.04 from 0.2 and get 0.16. This one plus 0.03. So 0 to 1 is that. So this one should get changed to 0.13. So I added 0.03 to 0.1. This one from 1 to 0, because it goes from 1 to 0, should have 0.04 subtracted from it. So I subtract 0.04 from that to get 0.26. And then this one currently has a size of 0.4. And then I add 0.3 to that to get 0.43. Okay? So now I'm going to do the exact same thing with the updating these links. Okay, so for example, this one right here is the weight that goes from neuron 1 to neuron 1, and it comes from layer 0. Okay, so I have to update layer 0's links. So I'm going to have 4 of those. Yeah, so this is really laborious to do this by hand. 0, 0, 0, 1, 1, 0, 1, 1. So I appreciate you staying with me. Okay, so my learning rate is 0.5. and then I have error in the layer in front. So now I'm looking at these errors, okay, following the second index. So second index 0, so my error is negative 0.07. Second is 1, so my error is 0.001. So here is going to be negative 0.07. Here is going to be 0.001, like so. So then I have the output of the second neuron, or sorry, of the second index in the layer in front. So these were the outputs of the layer in front of the 0th layer. Okay, so that's what these are referring to. So I have 0.58, and then this one would be 0.55. Here I have 0.58, 0.55. Okay, and then I have times 1 minus that, right? Times 1 minus that. So your second part of the assignment is going to be to automate this entire process. And then times the output of layer 0, okay, which is really simple because layer 0 does nothing. It just copies the input. So it's either going to be 0.8 or 0.2, depending on what the first index is. So I have 0.8, 0.8, 0.2, 0.2. Okay, so now I have to crunch the numbers one more time. So this one has a delta of minus 0.007. This one, so I'm just going to call that minus 0.1. This one has a delta of approximately 0. All right, because this number is so small. This one also is probably going to have a delta of approximately 0. Yeah, so this one also has a delta of 0. And then this one has 0.5, 0.7, a delta of negative 0.2. Okay, so what that means is that these two link weights are going to get reduced by very small amounts. Okay, so 0, 0. So this one should go to 0.29, and 1, 0. What's this one? Should go to 0.48. Okay, and then the other ones remain unchanged. So I subtracted 0.1 and 0.2 from, or this should be 0.01 and 0.02. I'm sorry. Okay, so now what I'm going to do is I'm going to redraw the neural network with the new weights. Okay? So we have 29.48. Now 1.7. Okay. We have 0 is 1.6. 0, 1 is 0.13. 1, 0 is 0.26. And then this one is 0.43. Okay. So now we're going to feed in the exact same signal that we did before, and let's see if it gets closer to the target output. Okay, so I'm going to go through this really quickly because I can imagine you're probably tired of watching me use the calculator. So so the input to this one is, this one has an input of 0.328. The input to this one is 0.22. Now I have to do the sigmoid on these to get the outputs. So this one has an output of 0.581. This one has an output of 0.555. So now we propagate it again into the next layer. This one has an input of 0.237. This one has an input of 0.314. So now I have to apply sigmoid on these again. Okay. I should have made my learning rate larger, I think. Okay, so what you saw is, so the previous output before we adjusted the link weights, okay, was 0.57 and 0.57. Okay, and remember the target was 0 and 1. So what we can see is when we adjusted the link weights, see how this output grew to get closer to 1, and this output shrunk to get closer to 0. Okay? So the idea is that learning, if the neural network is learning, we're giving it a bunch of inputs. Okay? Now I had stupidly set, when I did my math, the learning rate to a small number. And so what that means, and what you want to do is, if you have thousands and thousands of input-output examples, then you want the learning rate to be small because you have enough data points to really zero in on the target. And so, but that means that the output of the neural network doesn't change very much after a single example is given to it. Okay, but if I had chosen a larger learning rate, we would have seen bigger changes towards 0, 1. And so ideally, you give many, like thousands of input-output examples, and the weights of the neural network are adjusted gradually, and so it starts to zero in on the correct behavior. Okay, and so we're going to talk about training the neural network in the next lesson. So what I've shown you today is how do you take the error and back propagate it through the network so that each neuron has its own error. And then how do you use those errors to update the link weights so that the neural network, the next time it is run, will better model what you want it to model. Okay? So that's the lesson for today, and I will see you in the